a third observation that we can make is that you can also see that the angle of travel from layer to layer changes with changes in density. So for example, look at the wave that is labeled E. So this wave right here, right? And how it appears to travel faster through the outer core than it travels through the mantle. So you see it traveling here, then it changes speed and appears to be going faster based on the angle at which it's traveling, and then it reduces speed again once it reaches the other side of the mantle, on the other side of the outer core, right? So that's one other observation you can make. And lastly, another pretty cool fact is that waves reflect off of certain layers, as is the case, for example, in the set of seismic waves that are labeled C. So you're seeing here these two waves coming in at this angle and reflecting off once they get to the outer core, and also being received at the Ulaanbaatar station. So even though you have two sets of layers arriving at Ulaanbaatar, one of them didn't reflect at all. One of them simply got there. The second one did reflect off a different layer and got there a few minutes later. So 1 minute later for the P wave and 2 minutes later for the S wave. So that's another pretty cool fact that allows us to understand that there are subdivisions within the Earth. So overall, having this information available from those recording locations, and more specifically from the locations where both P and S waves arrived, allows us to pinpoint how far the earthquake actually happened. So we can calculate the distance from the recording station to the earthquake epicenter, meaning where it happened, up on the surface, by checking the time in between the arrival of the primary waves and the arrival of the secondary waves. And later we can see the layer subdivisions by the reflectance of certain waves and the recording of them at the seismographs. So how you do that, we will see in the next chapter, on chapter 3, when we go through that. And in fact, you will have as one of your labs for chapter 3, or the lab for chapter 3, you will have to do the checking how far the epicenter is from the recording stations, as you are provided the P and S wave arrival times, for example, amongst other things. So that's how seismology helps us understand the internal structure of the Earth. Okay, so linking the concepts of seismology that we just covered in the previous slide and of the internal structure of the Earth, we are able to understand certain aspects of plate tectonics better by the study of earthquakes. So again, by using seismology. So one of those aspects that we can understand better is where is the magma being generated from in the asthenosphere. So when we see, I'm going to draw. So when we see this diagram, we see that magma is being generated at 3 different spots, right? Which is where those circles pretty much are showing you. Let's make an example earthquake that has just happened, let's say, here. Okay? Okay. Near the sinking plate, right? So it's near this plate. We know that the primary waves released from the earthquake will travel through the magma body and appear somewhere else at the surface. So they will start traveling through this lithosphere right at an angle, slightly change in their angle once they get to the asthenosphere because it's a different density, and then change dramatically in their angle once they reach the magma body, right? Since it's a liquid, more buoyant, less dense form. So it's hard to represent by these drawings, but you get the idea. And eventually rise up to the surface. Let's say right here. Okay. But we also know that the secondary waves released from that earthquake will not travel through that liquid magma. So these were primary, the blue ones. But we know that the secondary waves will travel slower, but through the same path, But once they hit the magma body, they will stop their travel. So you will not receive them at the same location. They will not appear here at this recording station. Okay, good. And they will either again die off, like I showed right here, or they will reflect somewhere else. So perhaps they could have reflected somewhere here, right? Okay. All right. Another thing that we have learned from seismology, for example, relating plate tectonics, is that we now can see the slabs of lithospheric plates that have sunk deep into the mantle. So, for example, we can identify this subducting plate as it's deep within the mantle. So we can, applying this same concept of where the earthquake happened and how the seismic waves travel, we could see how fast or how slow the waves are traveling through that sinking slab here. So let's do that. So let's have our earthquake in the same location, but now we're going to have a recording station elsewhere. So we're going to say it travels kind of fast, then a little slower through the asthenosphere. Once it gets to the subducting plate, it's going to travel fast again, and then fast through this part right here. Or let me redo that. So fast through the through the lithosphere here, slower through the asthenosphere, fast through this subducting plate, slower through this section of asthenosphere, and then fast through this part of the lithosphere again. Okay, so there you can see that we can actually pinpoint where the subducting plate is because it is made out of lithospheric material that is more solid, and so you will see it at a different speed. The wave will travel at a different speed than it did through the asthenosphere over here. Okay, so hopefully that makes sense. We're able to pinpoint where those might be, how deep they may be based on the speed at which the waves travel. Okay. And a third thing, for example, that we can understand from seismology regarding plate tectonics is the variability of the lithospheric plate thickness. So using the same earthquake location again, the wave would travel shorter through this section of the lithosphere. So for example, it would travel shorter here than it would if we had it going through this whole area, right? So we also can find out how thick the lithosphere might be under certain locations. So again, if my seismic wave was fast, kind of slow, and then fast here, that means that this section, because of how thick it is, might make it that much faster than if we go through this section, which is thicker even. Okay, so basically depending on the speed at which the waves travel, we can also pinpoint the thickness of the material that they are traveling through, not just the type of material. Okay, so again, three things: where the magma is generated within the asthenosphere, where are the slabs of the lithosphere that are sinking deeper into the mantle, and the variability of lithospheric thickness. Those three things we can learn from seismology relating the plate tectonics concept. All right, so plate tectonics itself is a process. It's a large-scale geologic process that deforms the Earth's lithosphere. So by deforming the Earth's lithosphere, it causes landforms such as large ocean basins, like this one that you're seeing here, like continents, like this one that you're seeing here, like mountains, for example this one, or again the mountains could either be oceanic, like the one that you are seeing here, this is a big ridge, or they could be continental, like the Rockies that you're seeing right here. But you can also find things such as ocean trenches, like this very dark blue thing that you're seeing here, which are again very deep parts of the ocean, so deep and so steep that they're almost cliff-like areas within the ocean floor, and we'll talk about them as we go on. So these big processes of plate tectonics that are subdivided further, as we will see later, are driven by internal forces. One of these forces is convection, as we talked about a few slides ago. And then there are a couple forces that are also aiding forces, also related to convection, however. So those two are slab pull and ridge push, and we will talk about them later. And these are again driven by convection themselves. Slab pull and ridge push. So these forces allow material to move from side to side, direction to direction, and up and down within the depths of Earth. Each landform that the plate tectonics processes form is characteristic of a subprocess that is taking place. Okay, so for example, a mid-ocean ridge, like this one that is here, or this one that is here, is characterized by new material that is rising up to the surface when two different tectonic plates are moving away from one another. So in this case, this plate right here is moving to the right, this plate right here is moving towards the left, and so as they're moving aside from one another, material is rising up to the surface and filling in the gap and making that ridge in between them. So we'll cover this and other sub-processes in a lot more detail in the next few slides, so no worries if you don't quite get what I mean yet. So, as I had mentioned earlier, it was in the lithosphere that the plates actually were, or the lithosphere that they actually are. They're made up of lithosphere. Or rather, again, they're made up from this material. In fact, the whole lithosphere is split or broken up in two pieces, which we call the tectonic plates. Okay? So these tectonic plates can be oceanic or continental in nature, meaning containing mostly oceanic lithosphere, like this plate that you're seeing here, kind of subdivided, right? Or they can be mostly continental, for example, like the Eurasian plate is mostly continental. Or they can have a mix of both types of material. For example, like the African plate, which is somewhat continental, but it has some part of oceanic as well. However, the different plates will be mostly oceanic or mostly continental, even though they might have parts of one another. So the plates themselves are typically named after the land masses that occupy that space. But you see, for example, the North American plate does occupy most of the North American continent within it, but it also contains much of the western and northern part of the Atlantic Ocean, right? The same thing happens, for example, as I just mentioned, in the African plate. It is made up of the landmass of Africa, right? But it also contains much of the southern and eastern part, eastern part of the Atlantic Ocean as well, along with some part of the Indian Ocean and a little bit of the Antarctic Ocean. These plates will move relative to one another. So this one moves relative to this one moves relative to this one from this one, so on and so forth. And by taking these motions, material from the plates might be created, or by looking at these motions, the material will be either created, it will be destroyed, or it will neither be created or destroyed, but the whole plate might be shifting, basically. And we'll look at this in detail. So when I say that material is being created or destroyed, I don't mean that the whole plate will necessarily be, exhumed out of Earth all of a sudden, or that it might be a new plate will suddenly appear, but rather pieces at the edges or at the boundaries of the plates will be created, will be destroyed, or will simply be shifting relative to one another, okay? And we'll look at these again in detail as we go along the lecture.